Whole video is this one example. Hopefully you have the example written down. We're saying we've got a cannon on top of a 147 meter cliff. It's got a slight angle upwards of only 12 degrees. And we know the muzzle velocity. Muzzle velocity is, or speed, it's just how fast it leaves the end of the cannon. Okay, so again, neglecting air resistance, we want to find out dx, how far the thing moves horizontally, and the speed when it hits the enemy ship. Okay, so just my little picture here with my knowns. That's the good form, is to start by drawing a picture. A little bit out of scale if you look at my cannon compared to the enemy ship, and to the height of the cliff. So here it is on the end of the cliff. The dy is 147. Just a quick little thing, and this picture doesn't represent that at all, but we do, if you don't know otherwise, you can assume that the distance from the muzzle to the top of the cliff is negligible compared to the overall drop, which is 147 meters. Maybe to be more accurate, you could say 148. Maybe that's about a meter off the ground, but if not given, just give the information you have if you don't know. So here's its exit velocity, the vector that represents that, at a 12-degree angle above the horizontal. What I figured out over here in the triangle was the x and y components of that. So the x component is just the 462 times cos 12, okay, and the y component would be 462 sine 12. Now, notice, by the way, I'm using the same sign convention I chose last time, which is down as positive, and that does have to keep that in mind with what we call negative and what we call positive, because this velocity vector, this y velocity vector, is going to be negative because it's in the up direction. Okay, so you get the picture down. Oh, here's the water, and there's my dx, what I'm looking for, and we'll make out our table. If you need more time, just pause. So just to begin, x and y direction, let's look at the x. Again, there's only one formula, just write it down right away so you don't get confused. We know dx and we know vx because it's 462 cos 12, which works out to about 452. I'm guessing that's not exact. I probably should have put an approximately equal to on there. So that's 452. And that's, again, it's the only information. We don't know t, and we want to find dx. So there's nothing else I can do on the x side. So this problem is really working out to be a lot like the last question that we did, for part A anyway. So v1y is negative because we chose down as positive, and v1y is up. So it's going 96 meters per second in the up direction to begin. AY is positive because I chose down as positive, and dy is positive. So it does work out that this is the formula I'll use again, looking for time. I want to find time and bring it over here. Okay, it's the only useful formula I can choose. And so it's one of these ones where we have to use a quadratic, and you definitely did this last year. So I sub in d is 147, v1 is negative 96 times t, 4.9 is 1/2 of 9.8 t squared. And rearrange this to look like a, b, and c, right? 0 equals at squared plus bt plus c is the quadratic, the general form. And you sub into, and I didn't write it down, I don't care how you solve your quadratic formulas, if you do it in your calculator, if you do it in an app, if you do it by hand using the formula, whatever. You solve it as you wish. It does work out to two possible answers for time, and fortunately, we always use the positive. We choose the positive every time. Okay, if you're wondering what the 1.4 means, what does the negative time means, it kind of means, you might remember this in math class, it's like this is a parabola, right? And the idea is, you know, where's the start and the finish? So if I was going to finish up this parabola, where would it end? Right down here somewhere, and that's the minus 1.4 seconds. It's like, imagine if it was the full parabola, where would it have crossed here? Okay, we don't need to concern ourselves with that, though. It really just is take the positive root. Okay, then looking over to this side, sub in, and it's a big 9,000 meters, and I say, holy, that's big. I don't think there's a mistake in the formula, but it is a big one. Okay, so 10 kilometers away, but it's got a huge speed. I mean, 462 meters per second is huge, right? And most of that's horizontal, and it has to drop 147 meters. So, yep, 21 seconds in the air. Okay, so moving on, just look ahead to part B. I could put I should put my check mark on it. It's just that it's a big answer. Okay, part B is looking for, I want to know now the velocity of the ball when it hits the enemy ship. And so the velocity is right down here, right? It's on an angle, so it's going to have an x and y component. We'll solve for the overall. And yeah, that's what we have to do. So we'll go through really going, looking at this question then. So we need to know the horizontal and vertical components of V2. Well, we know the horizontal is going to be 452. It's the same as last time. That's not going to change. The vertical component is to use all the y data we have, choose one of the kinematics formula and solve for V2y. Okay, so then we can find, we'll know V2x because it's going to be the same as the initial. V2y, I chose this formula, but you could have chosen any of them, okay? V2y equals v1y plus ayt. You could have chose v2 squared equals v1 squared plus 2ad. Any of those would have worked because you have all kinds of information at this point. Well, I chose this one. I found it to be 110 meters per second down, positive, so down. And so then when I work out, like we've done so many times before, we know the x component, we know the y component. Let's solve for the magnitude of the v2 and the direction, the angle, below the horizontal. So numbers wise, it's 465. And which isn't that much different than it started, by the way. And then angle wise, 14 degrees. Okay, so this is, we've done this lots of times already. So then we have our final answer, 465 meters per second, 14 degrees below the horizontal. And done.